We're going to continue on here with chapter 6. So last time we were talking about bonding. We talked about different types of bonding. Again, there's ionic bonding. And ionic bonding is always between a metal and a non-metal. And remember, because of these sort of differences in their periodic trends, what happens when a metal and a non-metal get together is we always get a transfer of electrons from the metal to the non-metal, as the metal pretty much has all kinds of properties that pretty much makes them not want to hang on to their electrons. They're willing to give away their electrons pretty easily. And non-metals pretty much have all the opposite sort of characteristics. They have characteristics where they want to basically accept electrons, hang on to their electrons. The result of this is we get a cation, which is positively charged from the metal. We get an anion, which is negatively charged from the non-metal. And again, the importance of our ionic bond here is no sharing of electrons. It is that opposites attract that holds that together, sometimes referred to as electrostatic attraction, that positive negative ions there, attraction to one another. On sort of the other end, we have covalent bonding. And covalent bonding really is broken up into two types of covalent bonding. And first off, though, covalent bond is always between two nonmetals. And basically, we have polar covalent, or just a polar bond, or a non-polar bond. Covalent bond. And again, they both involve two nonmetals, and really because the nonmetals are in the same spot on the periodic table, they have very similar sort of properties in terms of what they want to do with their electrons. And basically what they both want to do with their electrons is hang on to their electrons and also bring electrons towards itself. So the best that they can do when they get together is some type of sharing of electrons. So in a covalent bond, we have sharing of electrons. In a nonpolar bond, we have equal sharing of electrons, like we saw with F2, I believe. And with not a polar bond, we have unequal sharing of electrons, like we saw with HF. Now, depending on whether the electrons are shared equally or unequally, results in two types of covalent bonds where there is sharing of electrons. One's a nonpolar bond, which you could kind of think of as being like a neutral sort of bond between those two atoms. There's going to be nice equal sharing of electrons. There really is no side of that bond that's more positive or more negative, because those electrons are really distributed sort of equally over the bond. And that's different than what happens in a polar bond. Because there's unequal sharing of electrons, the electrons really hang out more towards one element than the other within the bond. And it always will hang out towards the more electronegative element, which in this case is fluorine. And we can represent that with a very squiggly arrow. Not so supposed to be squiggly, but we have the arrow that points to the more negative side of the bond, and the back end that makes like a positive sign points to a more positive side of the bond. And that's what is sometimes referred to as a bond dipole. It creates a, as we think we talked about, a partially negative charge and a partially positive charge on the hydrogen in this particular example. And there are partial charges like we talked about last time, because there is still some aspect of sharing going on. So the electrons haven't completely transferred over like it happens in an ionic bond, where we get a complete transfer of electrons from the metal to the non-metal. Here, hydrogen is still barely hanging on, but he's still hanging on to those electrons. So there's some aspect, again, of sharing that's happening here. Whether it's a polar bond or a non-polar bond does affect other things in terms of these molecules, like how they interact with other molecules, as we'll talk about in some later chapters. What we use, as we talked about, I think at the very end last time, what we use to really help us determine how the electrons are going to be shared is electronegativity. And a reminder that electronegativity is the ability of an atom to bring electrons towards itself and on the periodic table increases as you go up and to the right and decreases as you go down and to the left. And it is fluorine that is the most electronegative element that you could have. And if you remember, we saw a table where there are some values that Pauline gave us for electronegativity, and we could take the difference in electronegativity values, and that's basically just subtracting the two values that we saw in that table, larger number from smaller number, so you end up with a positive number. And if the difference anywhere from like 0. Let's try that again, anywhere from 0 to 0.4, that's considered a nonpolar bond, which means we would expect equal sharing of electrons. Above 0.4, which is somewhere in the ballpark of 0.5 to below 2, that's going to be some type of polar bond, which means we would expect unequal sharing of electrons. And lastly, above 2, but not in all cases, it will be ionic. So as we talked about, I think at the very, very end last time, you really don't need the electronegativity values to determine an ionic bond. The two things that you need to figure out is there's a metal and a non-metal. You could check the ionic bond box right there. That's going to always be an ionic bond. So really you don't need it. You can use the difference in electronegativity values to help you figure out really covalent bonds is a lot of times what we'll use it for. And again, you could also use the general trend as I think we looked at last time. So again, if you're comparing something in terms of electronegativity that's in the same row, the guy further to the right would be more electronegative, and it should result in a polar bond. If you're comparing somebody in the same group, the guy further up in the group should be more electronegative, and it should result in a polar bond. So in a lot of cases, you can make a pretty good assumption as to whether or not you would have a polar bond just by using the general trend in electronegativity rather than the numbers if you happen not to have it. We also saw, though, that there are some diagonal sort of relationships, like carbon and sulfur, for example. Not drawn to scale there, but carbon and sulfur are diagonal of each other on the periodic table. They're not directly diagonal, they're kind of diagonal and over. So because carbon is further up, but sulfur is further to the right, they kind of cancel out their differences, and they actually end up with the same electronegativity value. So it is possible to have two different elements that could share the same electronegativity values, and that would result in a nonpolar bond because the difference would be 0, which is like perfect equal sharing of electrons. If you definitely have two nonmetals that are the same element, obviously it will be 0 as well and should be a nonpolar bond. But if you have a couple nonmetals that are sort of on that diagonal on the periodic table, it is definitely possible that they could end up with the same electronegativity values and result in a nonpolar bond. Remember that a kind of difference in electronegativity of 0 is sometimes referred to as a pure covalent bond, and that is still a nonpolar bond that is still equal sharing of electrons. That is just means that it is a perfect equal sharing of electrons in that particular case. Any questions on this? Thank you. That we talked about last time. Okay. All right, so as we saw with our examples there, again, atoms with really big differences in their electronegativity values will result really in an ionic bond. And that's why we pretty much know for sure when we have that metal and non-metal. A reminder, metals on the periodic table are to the left and non-metals are upper right. So we got things coming together that are very different in terms of those periodic trends. Usually will result in that transfer of electrons like we see in an ionic bond. And again, atoms with similar electronegativity values, that's our covalent bonding, because again, all the nonmetals are pretty much bundled up there in the same spot on the periodic table, which means they're going to have very similar sort of properties. So again, sharing is what we got going on in that situation. Here's a table again that describes what we were talking about. Less than basically 0 to 0.4, going to be nonpolar. Above 0.4 to below 2 will be polar, and again, ionic will be basically 2. Any questions on any of that there? All right, then let's talk about how to draw Lewis structures for covalent bonding and really covalent or molecular compounds. So these are the steps that you should follow when you go to write or draw a proper Lewis structure. And I would highly recommend you follow these directions because, it'll get you probably the right structure in most cases. The first thing that you want to do is figure out really how that molecule or compound is sort of put together. There are a couple of rules that help you decide maybe who should go where. In general, in the center is the least electronegative atom. So the least electronegative atom should be in the center of the actual molecule. That means by default, hydrogen wouldn't be there because, again, hydrogen should only have 2 electrons. So if you put it in the center, then it's obviously going to have more than 2 electrons. And fluorine shouldn't be in the center because it is the most electronegative atom. So those guys should definitely be on the outside. Once you have basically the logical arrangement here, you want to count up the total number of valence electrons there are present in the atom. So that, again, remember that the valence electrons equals the group number. So that is really the fastest way to calculate the number of valence electrons, is just to add them all up. If you happen to be dealing with any type of polyatomic ion, if you remember, polyatomic ions are groups of nonmetals that actually share electrons, but they do have an overall charge. So you will draw some of those along the way. You do need to add in the charges. So anything with a negative charge means that it has gained electrons. So you need to add that to your total. And anything that has a positive charge means it has lost electrons. So you need to subtract that from your total. Otherwise, you'll have the wrong number of electrons. Number 2 is probably the most important thing, other than 1, I guess. But number 2 is really important because when you are done, your picture needs to have exactly that number of electrons. It cannot have any less. It cannot have any more. It's got to hit exactly on that nose. We also want to think about electrons as not necessarily belonging to a particular element along the way. So sometimes people, when they go to draw Lewis structures, they try to do piecework. Like this guy's got 5 to start with, this guy's got 3. I want to kind of figure out how they all come together. And usually what happens is you will end up with the wrong picture, too many electrons, not enough bonds and stuff like that. So when we count up the total number of valence electrons, we want to think about just being able to distribute those electrons evenly to everybody so that the octet rule and everything is met. Once you have the total number of electrons, you pretty much want to draw a single bond, covalent bond, from the center atom to each of the outside atoms. Remember that one line represents 2 electrons. That will use up your total electrons that you calculated, or some of them. All the leftover electrons at that point should go on the outside atoms in pairs of dots until each of the outside atoms has 8 electrons, except for hydrogen, again, should only have 2. If you have filled up all the outside atoms with electrons and you made all your single bonds and you still have electrons, then you should go to the center atom and place those electrons also as pairs of dots. So you kind of want to fill up the outside and work your way in with the dots. It's at that point you should be out of electrons after you put some dots perhaps on the center atom. You want to make sure that everybody has met the octet rule. If not, then that is really where you want to kind of try to fix it by first making a double bond. And if that doesn't fix it, then you want to fix it by making a triple bond. So again, you do not usually want to kind of double bond or triple bond right out of the gate. You want to kind of save it to fix any situation where maybe the octet rule is not met. So let's take a look at one here together and see as we go through these steps. So if we want to draw nitrogen trifluoride, the first thing we're going to calculate is really the number of valence electrons, maybe. So nitrogen is 5. Again, the group number, there are 3 fluorines, each is 7. And that gives us 26 valence electrons. So once again, the 26 number is really important. We want to think about how this is arranged. And I'll be honest with you, most of the things in here is like one thing in the middle and everything's attached to it. Not in all cases, but a lot of times one thing in the middle and everything's sort of attached to it. Between nitrogen and fluorine, nitrogen is the least electronegative, so it should be in the middle. Fluorine should be on the sides. And by the way, it doesn't matter if you put the fluorine on the bottom there or if you put it on top, it's all the same and all works the same. Now that I have the logical arrangement, I got the total number of valence electrons. We're going to start with one single bond, which I'm going to use lines to represent between the center atom and the outside atom. And that's a grand total of 2, 4, and 6 electrons that I have used. That means I got about 20 more to put on my picture. They go on the outside ones, again, in pairs of electrons, which are dots. So that's going to be 2, that's going to be 4, that's going to be 6, that will be 8, that will be 10, that will be 12, 14, 16, and 18 at this point. At this point, I have placed on my picture a grand total of 24 electrons. I still have 2 more to go, and those 2 more will then go to the center atom as a pair of electrons here. And now we have placed all 26 of our electrons. The last thing that we want to do is make sure that the octet rule is met by everybody. So for our fluorine, it's got 2, 4, 6, 8. So that's good. 2, 4, 6, 8. 2, 4, 6, 8. And for our nitrogen here, we also have 8 electrons around it. And we'll use a different color here. Maybe that's a bad choice there. 2, 4, 6, and 8 electrons there around it. So that would be the correct. That came out purple. I like it. It's red on my screen, but it's purple up there. That would be the correct Lewis structure without all the scribble at the end there. That would be the correct Lewis structure. Any questions on those steps? Yeah. So the 26 was the total number of valence electrons in the entire molecule that we wanted to draw, and that came from the Lewis structure. The very first thing that I did is, or the very first thing you should do is just make a single bond to the center guide to each of the outside. Remember that each of these lines represents 2 electrons, so that is 2, 4, and 6 electrons that I had used at that point. And that left me 20 more that then should be filled on the outside until everybody on the outside has 8 electrons. And that we were able to use about 18 of those 20 on the outside. And then we still had 2 left. And at that point, we then would go lastly to the center to put those last 2. So you kind of want to work your way from outside in when you're distributing these electrons to get to your structure. Any question on that there? Yeah, you're welcome. Other questions? All right. So why don't you number of valence electrons? So nitrogen has 5. There are 3 oxygens, each are group 6. And we do have a negative charge here, as this is nitrate. Negative means that it has gained an electron, so we do need to add 1 to it. Otherwise, again, we will be a little bit short there. That's 18, 19, 24 electrons here. In this case, if we look at the periodic table, it looks something like this: nitrogen, oxygen. So we do know oxygen is further to the right in the same period. So nitrogen is the least electronegative. It should be in the center. We'll do an oxygen around. So once again here, we're going to basically just make 1 single bond from the center atom to each of those outside atoms. I'm going to get rid of this guy. It's going to be in my way. There you go. All right, so to do that here, we will go 1, 2, and 3. That's a grand total of 6 electrons I just used there. That means I got about 18 more to go. Those are going to go on the outsides as pairs. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I have put on 24 electrons. Is everybody good here? The nitrogen is not so good. It has only 6 electrons around it. All the oxygens are good. It's got 2, 4, 6, and 8, and they're all the same, all those oxygens, so they all have 8. Nitrogen has only 6. So we need to fix that. It does need, obviously, 8. So if I just put 2 dots, does that work? Does not work, because now I have a grand total of 26 electrons, which is too many. So we can't just put a dot. So this is, again, the situation where we tried to do it here single bonded, and it didn't get everybody to the octet rule. So this is where we want to make a double bond to fix that situation. So in this case, all of the oxygens are identical to each other. So it doesn't matter where you make the double bond. Can I just make the double bond by putting the line? I cannot, for the same reason. I now have 26 electrons. And by the way, the oxygen up on top now has like 10 electrons, which is too many. So that's not going to be good either. So when we go to make a double bond, what we are actually doing is we're going to take a pair of electrons, and we're actually going to be bringing those electrons in to make the double bond. So the result of that is we will end up in this case with a double bond up on top. We will still have our single bonded guys coming this way. And to make it pretty there, we'll put a little bracket and a charge around it there since it is an ion. And now the nitrogen has 8 electrons around it. The double bonded oxygen up on top still has 8. And our single bonded oxygens on both sides there also have 8. Any questions on that there? Yeah. Let's say we put the oxygen that's on top. It does not matter. Yeah. It's just like the molecule just turned. It's okay. Also, you could have double bonded to the right-hand side, which would give you a structure that looks something like this. So instead of the double bond being up on top, you could have did the exact same move there and put the double bond there on the right-hand side, and that would have been okay as well. And you could have, in this case, laid up that double bond on the left there. Doing the exact same thing, moving those electrons in. And you could have got this structure. These are all structures that are related to each other. These are all what are known as resonance structures. And resonance structures occur in this situation where you have basically more than one place where you could lay up that double bond. And that's because those double bond electrons are what are referring to as being delocalized, which means at any given point in time, you could really be hanging out at any of these oxygens along the way. So the true structure is probably somewhere between all those. And sometimes you will see resonance structures drawn, and it's usually indicated by that arrow there that's heading in both directions that these are resonance structures of each other. You don't have to draw all the resonance structures unless obviously you're asked to do so. If you were asked just to draw the Lewis structure, you could lay up any one of the 3 and they would all be correct in this case. Yeah. Where's the charge coming? The -1? The -1 is what that particular molecule has overall as a charge, although, so these are these polyatomic ions, which are actually nonmetals. So it's a weird concept. They are actually sharing electrons. But because of how they're sharing electrons and who they're sharing electrons with in terms of electronegativity difference of all the elements, each of those elements take on a sort of charge, if you will. So the short answer to your question is, for example, individually, each of those oxygens that are single bonded actually has like a -1 charge. And the double bonded oxygen there has a 0 charge, and actually the nitrogen in this configuration actually has a +1 charge. So if you add all that up, that's where the -1 actually comes from. In the case that it's beyond our class, we don't deal with that, but that's really where the -1 comes from. It's what is referred to sometimes as formal charge. So it's the sort of charge each of those elements will take when they're kind of sharing electrons in a covalent bonding situation. Other questions? All right. All right, so I did some, you do some, let's all do some here. Let's do a few more here just to make sure. So I think you got this guy next, which is this. So why don't you draw the Lewis structure for this guy? Why don't you also draw the Lewis structure for this guy? Why don't you do this guy? And why don't you do, okay, let's take a look, see how you're doing. So we'll start with the first one here. So we'll start with our valence electrons. So carbon has 4. There are 3 oxygens, each are 6. So once again, we have a -2 charge here, which means we do need to add 2 to our total. That's going to be 18. That's going to give us 24 valence electrons here. Carbon and oxygen, again, are in the same row on the periodic table. So carbon is the least electronegative, should be in the center, oxygen around. Once again, 1, 2, and 3 single bonds, which is 6 electrons. We're going to put the rest on the outside. So 2, 4, 6, 8, 10, 12, 14, 15, 16. That gives us a grand total now of 24 valence electrons. And again, in this case, if we look at it, we should hopefully see that carbon is not so good in this case. So just like the previous one, carbon is short. It only has 6 electrons. All the oxygens have 8. So once again, we do want to make a double bond to fix it. So we're going to take a pair of electrons and bring it in. And that's going to give us our double bonded oxygen here. And we will still have our single bonded oxygens on the other side. And once again, a little bracket and a -2. And this is another one that you could draw 2 other structures where obviously all you did was double bond to the other side. And those would be resonance structures. Any questions on that one there? Taking a look at the next one here, which will be H2S. So hydrogen is 1, so there's 2 times 1, and sulfur is 6. That is 8 valence electrons. We know hydrogen should never be in the middle, so that leaves sulfur as our middle candidate here. We're going to do a single bond to each, and that is 4 electrons that we've used. We now have 4 more to go. Do I put dots on hydrogen? No dots on hydrogens, right? Unless you want X's, so don't do that. So basically, hydrogen is good on the outside. It's got its 2 electrons that it needs. So now we need to go to the center atom, and we need to put those dots there. And in this case, everybody's good. We got sulfur with its 8 electrons that it needs. And again, hydrogen only has the 2 electrons. Once again, that is pretty much what hydrogen should always look like that. Yeah, just a line and an H, no dots, no double bonding, no triple bonding. Because if you do that, it is definitely wrong. Yeah, so do not do any of that. Any questions on that one there? Looking at the next one here, we got carbon, which is 4. We got 2 times 1, which is our hydrogen. And once again, our oxygen here is 6. So that's like 8, 12 electrons. So in this case, hydrogen cannot be in the middle. So that leaves us carbon and oxygen. And once again, if you look at the periodic table, oxygen is further to the right, which means it's more electronegative. So that means by default, carbon should actually be in the middle. Hydrogen should be on the outsides, as we know, and oxygen should be about there or down. It doesn't really matter in this case. And we will do our single bond. That is 6 electrons, which means we still have 6 more to go. And we will not be putting dots on hydrogen, so those are full, but we can still put some on the oxygen that's up on top. So that's going to be 2, 4, and 6. At that point, we have now placed all 12 electrons, right? Is everybody good in this case? It is not. It's actually carbon is short here. Carbon only has got 6 electrons. So we do need to make a double bond, and our only option in this case is the oxygen to do so. Obviously, we cannot make a double bond there to hydrogen. So once again, we're going to take a pair of electrons and bring it in, and that will get us something that looks like this. And now everybody is good. The double bonded oxygen has got 8 electrons. The carbon has got 8, and each of the hydrogens have 2. And again, only a grand total of 12 electrons in this case. Any questions on that there? Lastly, we have nitrogen, which is basically 2 times 5. That's 10 valence electrons. In this case, there really is no center atom because it's diatomic. So you can just put them side by side. By the way, you can still follow the same steps that we did before. We're going to connect them with a single bond. That's going to be 2. And we're going to put the rest on the outside. So that is 4, 6, 8, and 10 at this point. Are both nitrogens good? The one on the left is not. It's only got 4. So here we want to try to fix it by making a double bond. We're going to do the same thing and take a pair of electrons and bring it in. That will give us something that looks like this. Did that fix the nitrogen on the left? It did not. It got him closer. He's now got 6. So at this point, there's no other possibility for double bond. So now we go to a triple bond, and it works the same way. To make the triple bond, we're going to take another pair of electrons in to make the triple bond. And now we will end up with a triple bond and a couple of dots. And now are both nitrogens good? They are. And again, that's how nitrogen gets to a triple bond and still has those dots on the atoms. Any questions on the steps to draw Lewis structures? Again, if you follow these steps, you should end up with a pretty good picture. Yeah? If you don't follow these steps, you might end up with a bad picture. Yes. It does, because nitrogen is group number 5. So that would be how many valence electrons it has. And since there's 2 nitrogens, we times it by 2. Yeah. Exactly. Other questions? All right. There it is. All right, here. So let's talk a little bit about a couple other things here in terms of bonding, resonance structures, which we kind of talked about. But first off, bond length, and you don't have to memorize these numbers or anything like this. But if we look at a carbon-carbon single bond versus a double bond versus a triple bond, we see that the single bond is 154, the double is 133 picometers distance between the 2 atoms, and 120 there for a triple bond. If we look at carbon nitrogen, single, double, and triple, we see 143, 138, and 116. So the general trend is, as you keep putting more bonds on there, going from single bond to double bond to triple bond, the distance between everybody gets smaller. If you think about what we just did with our Lewis structures, to make a double bond, we brought electrons in from the outside to the inside, right? Which is going to make that negative charge big in between, going to bring everybody in. Yeah. So when we take a double bond to a triple bond, they're going to move in even closer. So a single bond is typically longer than a double bond, and a double bond is longer than a triple bond. And that also relates to strength as well. A triple bond is stronger than a double bond, and a double bond is stronger than a single bond. It's not like it's 3 times as strong or anything like that, but that is the general trend you see. So I sort of think about it like a brand new happy pencil out of the box, right? It's nice and long. If you wanted to break it, you could snap it with no problem. You take a chemistry test or 2, you got like a nubbin and an eraser left, right? And you try to break that, good luck, right? Very hard to do that because everything is together, right? And that's what happens when we come in for a triple bond. This distance between them gets very small, much stronger attraction now with those electrons in the middle, much harder to break than, say, a larger distance between those guys, which is much easier to break. Any questions on that there? So we cover resonance structures there as we were drawing, but resonance structures again develops when there really is multiple places that you can put a double bond. So for example, if we look at SO2, that is 6 plus 2 times 6, which is 18 valence electrons. And in this case, sulfur would be in the middle. Oxygens would be on the outside. And that's because if we look at sulfur and oxygen, they're in the same group on the periodic table. Oxygen is higher in the group, which means it's more electronegative. So sulfur should be in the middle. We'll do a single bond and a single bond there. And that is 4 electrons. So our 18 will go on the outside. So 2, 4, 6, 8, 10, 12. At that point, we have now put on there 16 electrons. We actually still have 2 more electrons to go. That is how they get to the center, by the way. Yes, there should be some dots on the center because that's where you should place them. At this point, everybody is good except for sulfur, only has 6 electrons. So in this case, again, we can make a double bond on either side. So if I were to first make a double bond coming in this way, we will end up with a structure that looks like this, where we double bonded over there. We could have easily just brought the electrons in that way to do so. And that would give us a resonance structure where the double bond would be on the left. And this is also a really good example as to why you should follow those steps, because most people don't follow those steps and they just lay up a couple of double bonds and put the wrong structure there because there should be non-bonding electrons on the central atom. So you do want to follow those steps of distributing the electrons so that everything comes out correctly in this particular case. Any questions on that there? And as I mentioned earlier, when we were talking about there with the, I think it was carbonate or nitrate, you don't necessarily have to draw all the resonance structures unless you're asked to do so. So carbonate is the one that we saw. And by the way, that is where the -2 comes from. Kind of a similar question. The -1 charge on each of those oxygens is where the -2 comes in for carbonate. This guy is basically 0, and this guy is 0 in terms of the charge. So that's actually where the -2 charge is actually being carried in the case of carbonate. Benzene ring that we will see a little bit later on when we talk about organic chemistry looks something like this. It is 6 carbons and 3 double bonds. Everywhere there's a point is a carbon. And it has 3 double bonds. You could draw a resonance structure like so as well. And as we will probably do it most of the time in this class, when we get into organic chemistry, a lot of times people will just draw like a little circle in the middle, and that indicates that those electrons are basically delocalized or moving around, and it could be really at any of those locations. So in our book, most of the time benzene will kind of look like that. In a maybe true organic chemistry book, it will look something like that with the individual double bonds sort of drawn out. Okay, any questions on resonance structures? So we talked about the octet rule, and you should definitely in this class always follow the octet rule. Everything that we draw in here will follow the octet rule, but you should also be aware that there are some exceptions to the octet rule. Once again, you will not be asked to draw any of the exceptions, but you do need to know what the exceptions are. But again, everything that we draw will obey the octet rule. The first sort of exception to the octet rule is what's referred to as an incomplete octet. And there are certain things that are okay with just less than 8 electrons. And most commonly, boron is the most common one that we come across. And it's electron deficient, and it's actually quite happy with 6, and it doesn't need any more really there as well. Beryllium and aluminum are included in that. But beryllium and aluminum usually will do more ionic bonding than covalent bonding. So boron is very commonly the one that you see for an incomplete octet. So one of the exceptions to the octet rule is an incomplete octet less than 6. The other couple of exceptions to the octet rule, again, that you should be aware of but will not be asked to draw, are odd electron molecules. So there are certain molecules that when you add up the valence electrons, you get an odd number. And if you get an odd number, that means you can't pair off all the electrons, and you have an unpaired electron somewhere. Maybe you've heard of free radicals. Yes, chlorine chemistry and the atmosphere does that. They have one unpaired electron. They're very reactive because of that. They don't really want that. They want to kind of fix that situation. So they're very reactive things that have these one sort of unpaired electrons. The most common sort of exception to the octet rule, if you were ever to take more chemistry, is the expanded octet. And we don't, again, deal too much with that here, other than you should know that it's an expanded octet. There are certain molecules that can go above 8 electrons, upwards of like 12 electrons around it. And those are usually elements where you find sulfur on the periodic table, kind of to the left and down. And if you remember, sulfur here is period number 3 on the periodic table, which is N is equal to 3. And on the third energy level, that is where we first see what orbitals? S, P, and that is where d orbitals appear. So because they actually have those d orbitals available to them, although they may not be using them, they can stash extra electrons, upwards of like 12 electrons. And that's where you go, periodic table, sulfur left and right and down could do that. So let me be really clear in here, you should not do that. Yes, so you should not Google answers to questions, because you will end up perhaps for sulfate, something that looks like this. Which is definitely more than 8 around that sulfur, but actually it's okay. It's actually the better structure. But we will know you Googled it because you're not supposed to draw that one. You're supposed to draw this one by following our rules. So sometimes it's not good to Google things. People know that you did because you shouldn't be drawing the other. Yeah. So if you follow our rules, you should end up with sulfate that looks like this. If you Google it, you might see sulfate that looks like that. So just a warning, don't Google things. Yes. Because you might not know what you're writing down, but the person who graded it might know that that's where you got the answer from. So We will not do any of these exceptions. You should always obey the octet rule when you're drawing things. But you do need to know the 3 exceptions. So an incomplete octet less than 6, an odd number of electrons, and an expanded octet that could happen at sulfur and kind of below on the periodic table because they have the d orbitals available to them. Any questions on that there? Yeah. So here to emphasize, not in here. Yes. Other classes, maybe, if you took another chemistry class. All right, so we're going to talk about molecular geometry here, which is known as Vesper. And molecular geometry basically describes how the molecule and the atoms are arranged in 3-dimensional space. We can predict sort of the geometry that we would expect based on our Lewis structure, and more so based on really the number of non-bonding electrons and the number of bonds, not really non-bonding electrons, the number of electrons and the number of bonds. When we do geometry, the most important atom is always the guy in the center. So the center atom is always the one that you want to look at. And really, there's 2 things you want to look at: the number of electron pairs there are. And that doesn't matter if it is bonding electrons or non-bonding electrons. So in your Lewis structure, it doesn't matter if they're dots, if they're lines. Those are, you want to count them all. And the number of bonds. And that is the most important thing here, is our number of electron pairs and our number of bonds. And we're going to talk about 2 types of names when we do geometry here. One is what is referred to as the electron pair geometry. And that describes how the electrons are arranged around the central atom in 3-dimensional space. The other geometry name is the molecular geometry, which is sometimes also referred to as the shape of the molecule. So these are 2 different names, and sometimes they are different names, and sometimes they are the same name, depending on the situation. But one describes just simply how the electrons are arranged around the central atom. The other one describes the overall shape of the molecule. So the basis, bless you, of this approach is the idea that we're dealing with electrons, obviously, in bonding. Electrons are negatively charged, which means, frankly, they don't really want to be near each other. So given the opportunity, what they're going to try to do is get as far apart from each other as possible. And in some cases, they obviously cannot escape, otherwise there would be no bonding happening, but they will try to arrange themselves as far as possible. And that's what gives us really the different geometries that we see. And this sort of method is what is known as Vesper, which is the valence shell electron pair repulsion model, hence the abbreviation. That is a mouthful. And basically, there's 2 types of molecules. It's when you draw your central atom and there's no non-bonding electrons, so no dots, and ones where you do have non-bonding electron or dots on your central atom. And depending on what sort of electrons are there, basically will determine sort of the names that we end up with. The really main rule for us is this first one: if you have a double bond or a triple bond, when you're doing geometry, it counts as 1 electron pair and 1 bond. So that's really important only for geometry. If you drew something that is a double bond or a triple bond, it effectively is working as a single electron pair and also a single bond. So let's take a look at this and see. We'll start with really the simplest molecules you could have, and those are diatomic molecules. And diatomic molecules do not have a central atom. They have just 2. And the only way you could arrange 2 atoms is basically a straight line. So whenever you have anything that is diatomic, the geometry is always going to be linear. It doesn't matter if it's 2 of the same, doesn't matter if it's 2 that are different. That guy would be linear. It doesn't matter if the 2 have a double bond, would be linear. Doesn't matter if the 2 has a triple bond, will be linear. If you see 2, it's linear. Move on with your life. Yes, and on that point. So when you have only 2, and again, it doesn't matter, like I said, if they're the same, they're different, single bond, double bond, triple bond, it doesn't really matter. It will always have the linear geometry because it comes down to the same thing. you basically have two things. The only one to connect them basically is a straight line. So you get that linear sort of arrangement. Now, when you have things that have 3 or more atoms involved, there should be a center atom. And again, that is always what you want to look at, is the guy in the middle. And you want to count up the number of electron pairs and the number of bonds. So let's take a look at the first sort of example of that. Here is an example of a central atom. And what we want to look at here is the central atom. And again, the two important things to count is the number of electron pairs, which in this case is 2. And that is the bonding electron, the lines that we see. And the number of bonds, which are also 2, which is again here and here. When we have 2 electron pairs, the electron pair geometry name, and from this point on, I'm just going to call it EG, is linear. And because both of those electron pairs are bonds, the atoms move with it. So the overall shape of the molecule is also going to be linear as well. So the molecular geometry are the shape. And once again, I'm just going to call this Mg from now on, is also going to be linear. What happens is basically those guys end up 180 degrees from each other. Those bonding electrons do not want to be near each other, so they just go opposite sides of each other as far away as possible. And that ends up in a 180-degree bond angle and a linear geometry. So in this case, both the electron pair geometry and the molecular geometry are both linear. And that's when you have 2 electron pairs around the central atom and 2 bonds. Any questions on that there? The next sort of example that we want to look at is one where we have 3 electron pairs and 3 bonds around the central atom. So if we look at BF3, our boron here has 1, 2, 3 electron pairs and 1, 2, 3 bonds. And again, always the guy in the center. So something with 3 electron pairs around the central atom, the electron pair geometry is going to be what is known as trigonal planar. It is also sometimes referred to as triangular. And because all of those electron pairs are bonding electrons, pretty much the atoms move with those electrons. And the molecular geometry will also be, in this case, trigonal planar. And that is because, frankly, it makes a nice, pretty triangle. Yeah, an equilateral triangle, basically. In this case, they cannot get 180 degrees apart because there's a third atom involved. So with that third atom, all 3 of those atoms got to keep kind of moving until they could kind of get as far away as possible from each other. And the best that they could do in this case is a corner basically of a triangle, which is why it's sometimes referred to as triangular. It has a bond angle of 120 degrees. By the way, the bond angle is based off of the electron pair geometry, is where the bond angle is based off of. Any questions on that one there? The next sort of example is a central atom where we have a very badly done thing there. I'm not really sure. I think it looks better on your paper, so let me redraw it over here. So it should look something like this. So if we look at the central atom, which is the carbon, it has 1, 2, 3, and 4 electron pairs. And it also has 1, 2, 3, and 4 bonds in this case. And something with 4 electron pairs, the electron pair geometry name is what is known as tetrahedral. And once again, all of those electrons are in bonds, which means there's atoms. So as these non-bonding, as these electrons move, because the atoms are attached, they move exactly the same way. And they end up with a molecular geometry of also tetrahedral. And that's what you see here. It's kind of like a triangle on the face and more of a pyramid type shape on the bottom. And it has a bond angle of 109.5. Up until this point, both the electron pair geometry name and the molecular geometry name are exactly the same. And that is because the only type of electrons that we have on the central atom are bonding electrons. And again, because they're bonding electrons, as those electrons move, so does the atoms, and the overall shape ends up the same as the electron pair geometry. So whenever you have a Lewis structure where you have no dots on the central atom, both the electron pair geometry name and the molecular geometry name will always be the same, because the atoms move exactly how those electrons move. It is only when we introduce non-bonding electrons to the mix that we now have different molecular geometries. So when non-bonding electrons and you have dots on the central atom, it's actually the molecular geometry name is the name that changes. And that's because it is missing an atom that would normally be there. It has just the dots, the non-bonding electrons. And that gives actually the other atoms a little bit more room to move about, because they don't have that extra atom moving around with them. So they're able to kind of spread out a little bit more. And what that ends up affecting is the molecular geometry name. So let's talk a little bit about some of those examples here. And when we have electrons in sort of a Lewis structure, there's three types of interactions. Really, the best interaction is when we have bonding electrons near bonding electrons. So on your Lewis structure, lines near lines, that's an okay sort of interaction. The next sort of best situation, which is getting kind of a bad situation, is where you have non-bonding electrons near bonding. So in your Lewis structure, you got dots and lines happening on the central atom. The really worst case scenario is where you have non-bonding electrons near non-bonding electrons. So in your Lewis structure, dots near dots. They try to get as far away as possible. And again, as these non-bonding electrons are moving, the guys that have the atoms attached are also going to move away from those guys. And again, that's going to affect the molecular geometry of that particular compound. So let's take a look at some of those here. And if you don't worry about the letters and stuff like that, it's not that important. So if we look at an example like our guy that we just drew, which is sulfur dioxide. And if you remember, sulfur dioxide looks something like this. We will look at our central atom, which is sulfur. And in this particular case, we want to count up the number of number of electrons. So that is one electron pair, two electron pairs. Double bond counts as only one. So this guy would have 3 electron pairs. Once again, it does not matter if they're dots or lines, but it has 3 electron pairs. Yeah. The number of bonds that this guy has is 1 bond. And once again, the double bond will count as only 1. So it'll actually have 2 bonds. So as I mentioned earlier, the number of electron pairs and electron pair geometry doesn't change. So as we saw earlier, something with 3 electron pairs is our trigonal planar. But what happens in this situation is these non-bonding electrons go up, and these guys decide we want to kind of get away from them. And what ends up happening is we get this, what is referred to as an angular shape. That makes this angular type of shape. So the molecular geometry is angular. Some books will still call it bent, and some books will call it bent angular, depending on your book. And it has a bond angle of less than 120 degrees. And again, because of these non-bonding electrons on top, there's not an extra atom to kind of get in the way. So it's able to get further away from one another and create this angular sort of geometry. Questions on that there? The next example of geometry that has non-bonding electrons is where we have a central atom and 3 things attached and some non-bonding electrons sort of happening. And that is an example of NH3. And when we look at NH3, we look at the central atom. It has 1, 2, 3, and 4 electron pairs. But it has only 1, 2, and 3 bonds. So once again, something with 4 electron pairs, like we saw earlier, the electron pair geometry is still going to be tetrahedral. And kind of a similar idea, these non-bonding electrons kind of go up. All these bonding guys kind of go down, and these guys are trying to keep their space from one another. and it creates a molecular geometry known as trigonal pyramid. And that's because it kind of makes a triangle and a pyramid type shape happening there with our non-bonding electrons that are occurring. The bond angle here is less than 109.5, which is our tetrahedral bond angle. And because we're missing that fourth sort of bond there, it's able to kind of move a little bit more than it can with that extra atom present. Now, speaking of trigonal planar and trigonal pyramid, those are two different names. So trigonal planar is 3 electron pairs and 3 bonds. Trigonal pyramid is 4 electron pairs and 3 bonds. You should pick. You should not just write trigonal because I'm going to mark it wrong. Yes. So you got to choose planar or pyramid, and you can't write my other favorite trigonal. That's clearly pyramid. I mean planar. Which one is it? I'm not really sure right there. Yes. Don't let me choose. I failed chemistry, so I will choose wrong. Yes, with an X. So make sure that you choose which one. Don't just write trigonal for either one of those. Either do planar or pyramid. Any questions on that one there? And the last geometry that you are responsible for is the one that we see with our friend water here. And if we look at water, at the oxygen, it has 1, 2, 3, and 4 electron pairs. And it has 1 and 2 bonds. So just like we just saw on the previous slide, something with 4 electron pairs, the electron pair geometry is still tetrahedral. But in this particular case, we actually have all of the worst things happening at once. We have bonding electrons near bonding, we have non-bonding near bonding, and we have non-bonding near non-bonding electrons. So what happens is these non-bonding electrons try to get as far away as possible, while these bonding electrons also try to get away. And the result of that is a molecular geometry known as bent or V-shaped. And that is why we're going to use bent or V-shaped here and angular for the other one. The bond angle here is less than 109.5. It's about a $1.04, 104 in terms of the percentage there. So for us, the best way to know it is really just to memorize and make a table, number of electron pairs, number of bonds, and the molecular geometry name. You'll be responsible for lecture for just the molecular geometry name, so not the electron pair geometry name. So you're responsible for just these names here on the right there for lecture. There is a table that's in your book, looks something like this, and it's kind of based off of what we just talked about. So once again, you are responsible for the molecular geometry names here, which are these guys, should be this guy, the shape. Any questions on geometry there? Up this chapter here. So any questions on geometry? So once again, for lecture, it is just the molecular geometry that you're responsible to know. And really the best way to do is kind of go back to your slides you want and make a table, number of electron pairs, number of bonds, and the geometry that goes with it. Most people cannot visualize it three-dimensional in their head, myself included. So that's really the best way to sort of do it. The last thing we're going to talk about here is molecular polarity. And molecular polarity is the molecule as a whole, whether or not the entire molecule shares electrons equally or unequally. We talked about bond polarity, where we use the difference in electronegativity values to determine whether or not we had a polar bond or a non-polar bond. Now, when we are dealing with a polar molecule or a non-polar molecule, and we're trying to determine that, if it is diatomic, those are really the easiest molecules that you can determine. So for example, if we had our F2 that we saw earlier, we know that they both have really the same electronegativity value, 4 and 4. So if we subtract it, that gives us a 0 for the electronegativity. That means that this bond right here is a non-polar bond. And because this molecule is diatomic, that is the only bond that's present. And because it's the only bond that's present, the molecule itself needs to be non-polar. So that would be a non-polar molecule. Just like if we looked at HF that we saw earlier, we know that this is a polar bond and F being more electronegative. So that is a polar bond. And because this is the only bond that's present in that molecule, this molecule would be a polar molecule. And polar molecules have what are referred to as a dipole moment. And what that means is there is a side of the molecule that's more negative, and there is a side of the molecule that's more positive because of the unequal distribution of electrons overall in that molecule. So diatomic molecules are really the most simplest one to determine whether or not the molecule itself is polar or nonpolar. And basically, if you could determine if the bond is polar or nonpolar, then the molecule will be the same because, again, it only has one bond. So whatever that bond is what the molecule itself is. Now, when we are dealing with three or more atoms in a molecule, you actually have to look at two different things. So it does get a little bit more difficult when we're dealing with things that are not diatomic. So when we do have three or more atoms involved, you have to look at, is there polar bonds? And if the answer is there is no polar bonds, then the molecule is nonpolar. If the answer is yes, there is polar bonds, then you have to look at the molecular geometry or the shape. So if there's no polar bonds, then the molecule will be nonpolar. If there are polar bonds, when you have three or more atoms involved, you need to look at the geometry of it. So for example, if we look at carbon dioxide, which looks something like this. Carbon dioxide has polar bonds, carbon and oxygen. The oxygen is more electronegative, so it actually does have polar bonds. And we could draw those bond dipoles pointing towards the oxygen as it is more electronegative. So you might think, well, it has polar bonds, so this molecule should be polar. The second thing we have to look at is the geometry here. So how many electron pairs does this thing have? This has 2 electron pairs, right? Each double bond counts as 1, and it has 2 bonds. So the molecular geometry of something with 2 electron pairs and 2 bonds is linear. And what that essentially means is you can think of it like this pen. I have oxygen on one side pulling, and I got oxygen on the other side pulling the other way. Is my pen going anywhere? It is not. I'm actually really pulling in this case. And my pen is actually not going anywhere. And it's because they actually cancel each other out. So although something like CO2 does have polar bonds, because of its geometry, they actually will cancel each other out. And this is going to be a nonpolar molecule. And that is because those dipole arrows here, those are vectors. They have direction, they have magnitude. And then I fell asleep in physics and I woke up long enough to remember that in some cases they add to each other, other cases they cancel each other out, and in this case they actually cancel each other out. So whenever you have those arrows heading in equal and opposite directions, they cancel each other out. And also if they're heading directly at each other, they will cancel each other out as well. Now if you took something like water, water also has polar bonds. The oxygen is more electronegative, so we could draw our bond dipoles heading in this direction. So it does have polar bonds. As we just saw a second ago, the central atom here has 4 electron pairs and 2 bonds in this case, which means the geometry here is bent or V-shaped. In this particular case, the dipoles are going in this direction and they kind of meet at the top, like you're going to pull from the top, and you can imagine everything moving. In this case, they actually will add to each other, and you will get what is referred to as a net dipole moment, which is the same arrow. And in water, the oxygen is more negative, the hydrogen is more positive, because those guys will actually add to each other. If you want the physics explanation, you go head to tail on these things, right? Then you meet them guys in the middle, like so. Yes, they add to each other vector-wise. Nobody wants to do vectors at all. But in this case, this would be a polar molecule. because of the geometry here. And only polar molecules have a dipole moment. So a dipole moment is just the same arrow, and it's just telling you in this case, all the electrons are hanging out by the oxygen, and the hydrogen and water has less electrons hanging out on that side. So we have an unequal distribution of those electrons as a whole. So when you have 3 or more molecules, it's really important to look at the geometry and also whether or not there's polar bonds, but nobody wants to do all that. So there must be a quicker way. So let's do the quicker way, perhaps. There are certain symmetrical geometries. And symmetrical geometries for you guys, when we remember which ones you got going on. This is trigonal planar. And these are molecular geometries we're talking about here, and tetrahedral. And what both of these have in common, if you remember what the Lewis structures look like, they have no dots on the central atom, which basically means there's no non-bonding electrons. They're all bonds. And if you have this arrangement and all the atoms are the same on the outside, it will be nonpolar, the molecule, because they will all be equal and opposites of each other, and all those dipoles, even if they have polar bonds, will cancel each other out, and you'll end up with a nonpolar molecule. So for example, if I took something like this, I won't draw all the dots on the fluorines, but there are dots there. This has polar bonds, the fluorine being more electronegative. So the arrows would all draw out towards the fluorines, but because this geometry is symmetrical, they all end up being equal and opposite of each other where those fluorines end. So again, it's like kind of pulling on a rope. Everybody pulling on a rope equal and opposite. Rope's not going to go anywhere, right? So they all cancel each other out, and this would be nonpolar, the molecule. Now, what would happen if I took something like that and swapped out one of the fluorines for a hydrogen? Now, in this case, I have polar bonds heading this way and this way and this way, and the carbon-hydrogen bond is actually nonpolar. So you could kind of imagine everybody on this side is pulling this way, and this hydrogen is not pulling the other way. It's actually going with it a little bit. So you can kind of imagine if everybody kind of pulled in that direction, the whole thing would move, and it will now become polar, this molecule. So if you have a symmetrical geometry where everything on the outside is the same, no dots on the central atom, is going to be nonpolar. If you swap out one of those atoms for something different, and they're not all the same on the outside, it probably is then going to become polar. Any questions on that there? That leaves us unsymmetrical geometries, and unsymmetrical geometries are ones where we do have dots on the central atom. So let's get rid of some of this here. So for you guys, in terms of unsymmetrical geometries, you got a few, I think. You have your angular, you got your trigonal pyramid, you got your bent or V-shaped. And what all these have in common is that central atom is going to have some dots on it, or non-bonding electrons. And if you have this geometry and everything is the same on the outside atoms, you will get a polar molecule. So that pretty much only leaves linear as the one you have to think about, and that's pretty simple. If you have a linear and they're going opposite, they will cancel. If you have linear and they're heading right at each other, they will cancel. But it is possible to have linear where everybody's heading in the same direction in terms of electronegativity, then it would be polar. So for example, if we look at some of these ones that we drew, and we'll see how fast you should do molecular polarity here. I just draw a bunch here and see here. All right. So we'll take our this. I won't draw all the electrons in, but we'll just quickly sketch some here. That's the one we just did there. All right, here we go. Let's see. We want to know, are these guys polar or non-polar molecules, right? And we'll add one more here. We'll do this. All right. All right, so starting here, I see dots. Yes. I see the same atoms on each side, polar or non-polar. Polar, yeah. Here, I do not see dots, but this is linear. So this is the one we just did. This is going in opposite directions. So because of geometry, it will also be non-polar in this case because they will cancel. This one, I see dots. I see everything on the outside is the same, polar or non-polar. Polar, yes. Dots, everything the same on the outside, going to be polar. How about this one? I see no dots. Everything on the outside is the same. It is non-polar based on geometry. This guy right here is diatomic. So I'm looking at that bond is non-polar, right? So this guy should be non-polar. This one, no dots. Everything on the outside is the same or different? Different. So it should then be polar. Yes. Again, they would be non-polar if they were all the same. Yes. So in this case, they're not all the same. So they becomes polar. This guy here, no dots. Everything on the outside is the same. It's going to be non-polar, regardless. The carbon-hydrogen bond's non-polar to begin with, so it would be non-polar as well. That is how fast you could do molecular polarity, and you'll probably be right most of the time. Yeah. So basically, you can break it down to Lewis structure: dots, no dots. If it's no dots, everything's the same. Probably a safe bet to go non-polar. If there's no dots, everything is not the same. Probably also a safe bet to go polar. And if there are dots on the central atom and everything's the same, probably a safe bet to go polar. I'll go 98.5% of the time you'll be correct. I think that's pretty good, but maybe 99. Yeah. Any questions on molecular polarity here? Yes. No. Question. This one here? Is that the one? Yeah, it's because we have no dots on the central atom. And basically the geometry of this is trigonal planar, which means basically all those oxygens end up in a corner. And that's equal and opposites of each other. And even though there are polar bonds, that's going to give you that symmetrical, everybody pulling equally on the rope, and it's not going to go anywhere in that case. Other questions? All right, that wraps up this chapter. Okay, so here in chapter 7, we're going to talk about chemical reactions. We're also going to talk about chemical quantities, which is calculations involving reactions as well. So we're going to start with actual chemical equations. And chemical equations are used to represent chemical reactions. And chemical reactions are a chemical change that occurs. What we start with and what we end with are two different things. So above shows a balanced chemical equation. And there's really two parts to a chemical equation. The left-hand side of the arrow are what are known as reactants. Those are really your starting material in a chemical reaction. Remember that in a chemical reaction, the only thing that happens is basically bonds break and you remake new bonds on the other side of the arrow. And on the other side of the arrow, which is this side, the right-hand side, those are our products, which are always found on the right-hand side of the arrow. There are other things that we sometimes will see in actual equations and things like states. So we'll commonly see S for solid, liquid, gas, or aqueous. And these things are oftentimes written next to the formulas in a chemical equation. Aqueous stands for basically a water environment. And basically those are solutions that are made. And there is a difference between liquid and aqueous. Liquid is a pure liquid like water. And if you take something like sodium chloride, which is a solid, and dissolved it in that, you would get a sodium chloride solution, which would have the aqueous symbol. So aqueous usually means that you took something and like dissolved it in water, and that is what the difference is between aqueous versus something that's a liquid. A liquid would be just a pure liquid by itself, nothing else in there, a pure substance. Other things that we sometimes will see is on top of the arrow, a catalyst is sometimes written. So that could be like a metal written up there, like platinum. It could be something like H+, which is an acid catalyst. And a catalyst is not a reactant. It is not a product. And it does not get used up in the reaction. A catalyst is usually there to speed up the chemical reaction. So it finds a way to sort of a more efficient way for those reactants to come together to make products, be it if it's a metal catalyst, for example, and you have gas molecules flying around. Without the metal catalyst there, those gas molecules got to fly around, try to find each other for the reaction to take place. If you have like a metal, for example, those gas molecules may be attracted to the metal, and that now puts those guys near each other. So that's going to allow them to start reacting a lot faster than they would if, they're just kind of flying around trying to find each other. So catalysts are really, and I'll find an alternative pathway for a reaction to basically take place. This is a balanced equation, which means we always start with and end with the same number of elements on each side of the arrow. So in this case, there are 4 hydrogens on the left, and that is 2 times 2 is 4. And there's also 2 times 2, 4 hydrogens on the right-hand side of the arrow. On the left-hand side of the arrow, there are 2 oxygens. And over here, 2 times 1 is 2 oxygens. So we have the exact same number of elements on each side. And that is because in a chemical reaction, it is only electrons that are involved. So we don't do anything with new protons, which is what, as we talked about, make the element what it is, right? So since protons are not involved, the elements stay the same in a chemical reaction. And we have really that conservation of elements as it happens. Any questions on that there? So whenever we deal with an equation, it should always be balanced. So let's talk about some steps of how to go about balancing equations. First off, sometimes you may be given the equation in words, and the first thing that you want to do is make sure that you get the correct formulas down, just like we did when we talked about naming. You want to make sure you start with the correct formulas, regardless of the balancing part. And then you want to balance. So that is the proper way to do it, especially as well if you're trying to predict what's on the product side of the arrow when you have nothing there. Very common people try to balance and write the chemical formulas together, and they end up with chemical formulas that don't exist, and they'll never be able to balance the equation because they don't have the right chemical formulas. So 100% of the time, if you're starting with nothing, but you need to write the formulas, forget about the balancing part, just get down all the proper formulas first, based like how we did when we talked about naming, and then go back and balance it. So that is the proper order to do that. It will make your life easy. You want to begin with the most complicated one. And when we balance equations, we actually only change the coefficients. And those are the numbers that come in front of the symbols. So we only change coefficients. We never change the subscripts, because if we change the subscripts, we just change what it is. Yes. So we never change those little numbers on the bottom. By the way, we also never, put a number between 2 things as well. So always in front is the only thing that we change. When you do that, you're basically going to put some coefficients on each side. Perhaps at some point, you should hopefully have the same amount of each of those guys on each side. And that would be your balanced equation. When you have balanced equation, you want to make sure 2 things happen. All the coefficients are whole numbers, and the simplest set of whole numbers. So what does that mean? That means that, let's say you balance this equation, 2a plus 4b gives you 6c, and we'll just say it's balanced. I could do what with all those coefficients? I could reduce them all down by 2. So this would not be the properly balanced equation. You should go through and divide out and get the properly balanced equation that looks something like this. So this sometimes happens because people see bigger numbers than other people, and it's possible to balance an equation with 2 different sets of numbers, but it does need to be the simplest set of numbers. So if you could go back through and reduce down your coefficients and still get whole numbers, you should do that, because otherwise it's not really a properly balanced equation. Any questions on that? All right, so let's take a look at one here and see. All right, so we have an equation like this and we want to balance it. Here is my approach. You could use it if you like. I'm going to rewrite this equation because I don't have enough room to put numbers in there. So that might be good. I personally like to make some tables, at least when I'm first starting to learn to balance equations. So what I have is the reactant side. I got the product side. I'm basically just going to list the elements. I got nitrogen, oxygen, and hydrogen. So on the left-hand side, I have 1 nitrogen. On the right-hand side here, I have 2 nitrogens. On the left-hand side, I have 1 oxygen. Right-hand side, I have 1 oxygen. Left-hand side, I have 2 hydrogens. Right-hand side, I have 2 hydrogens. So this is where I'm starting. It also helps you maybe focus where you want to start. Personally, once you look at a table like this, just start with what is easiest to fix, right? So we're going to fix it by putting numbers in front of everything. So in this case, oxygen's balanced and hydrogen's balanced. So really in this case, nitrogen should be where we should start. I could fix nitrogen simply by putting a 2 over here on the left-hand side. And I'm going to put a 2 in front of the nitrogen on the left-hand side. I'll put it as blue, 2. Now, when I put that 2 in front of the nitrogen, that nitrogen gets multiplied to everybody behind it. So that means I have now 2 nitrogens. I also now have 2 oxygens, and I still have 2 hydrogens at this point. Yeah. This is very common. As you go to balance an equation, you'll screw up something else, fix something and screw something else up. Eventually, it all should fall into place, hopefully. Well, clearly now oxygen seems like a good place to go next, right? And that's sort of the benefit of the table here. It kind of directs you where you maybe should go next. So to fix the oxygen on the right-hand side, I need to put a 2 in front of the oxygen on the right-hand side. And that would be this guy right here where the water is, right? That 2 goes to both of these guys behind it. So that will give me now 2 nitrogens. 2 times 2 is 4 hydrogens. And 2 times 1 is 2 oxygens. So I'm getting closer, right? I now got my nitrogen and oxygen in place. Last place I should go now is to the left-hand side. And what should I put in front of the H2 is a 2. That gives me, once again, 2 nitrogens, 2 oxygens. And again, 2 times 2 is 4 hydrogens. And this would be the properly balanced equation. Don't overcomplicate it. Yeah, just a big, simple. Yeah.
So we only balance the two front.
You could only change the coefficients if you want to do it correctly. Yeah. So you can, for example, for H2O, if you change that 2 on the bottom, it's no longer water, so you can't touch it. Nor can you put a number between like the hydrogen, the oxygen, a big number or anything like that. So it's always got to be the number that comes in front, and that number that comes in front gets distributed to anybody behind it. And again, as we talked about, right, when we have a formula like this, the number on the bottom goes to the guy on the right, or on the left. And if there's nothing written, it is assumed to be 1, right? So that again is where the 1 comes from. Yeah. We'll talk about it a little bit later on in this chapter. So for now, you don't have to worry too much about that. But for example, nitrogen and hydrogen are gases. That's just naturally how they come. And some of the other stuff you might not know. Other questions? All right, let's take a look at another one here. Why don't you give this one a go? Balance up this one and see what you come up with here. Again, only the numbers in front change. Again, I would recommend, since you're maybe just starting out, tables are helpful to kind of keep you on pace in a lot of cases. So just going to list the elements: carbon, hydrogen, and oxygen. So on the left-hand side, we have 3 carbons. Right-hand side, we have 1. Left-hand side, we have 8 hydrogens. Right-hand side, we have 2. 2 oxygens on the left. And how many oxygens do we have on the right? We have 3. We have 2 there plus 1 more over here. So that is 3, right? So we want to make sure we count it correctly. At this point, probably the simplest thing to start with would be carbon. We could really fix that pretty easily by just putting a 3 over here. Once again, when I put that 3, it goes for everybody that's behind it. So that would give me 3 carbons. That's going to give me still 2 hydrogens. Now, in terms of oxygen, I have 6 from the first guy, and I still have the 1 back here, which means I am at 7 in terms of oxygen at this point. Any questions on that? Yeah. Now, to me, the next simplest thing to fix is hydrogen. Why is oxygen not probably the simplest thing to fix? Oxygen on the right-hand side, it's in a couple of things, right? And on the left-hand side, it's in one thing. Hydrogen's in one thing on each side, so that is much easier to kind of fix and save that guy there for the end, perhaps. So I'm going to go with hydrogen next. To fix it, I could just put a 4, and once again, that is going to be distributed to everybody behind it. And that gives me 3 carbons. Hydrogens, 4 times 2 is 8. Oxygens, I still have 6 here, but now I got 4 happening over there. And that's a grand total of 10. Yeah. Any questions on how I got to 10? At this point, I clearly don't want to touch anything on the right-hand side, right? Because that's going to screw up everything. So the next easiest thing to fix now will be, go to the left-hand side and put a 5 right about there. That will give me 3 carbons, 8 hydrogens, and 5 times 2 there is 10 oxygens. So that would be our balanced equation. Yeah. Any questions on any of that? At some point, as you're putting numbers down, things should kind of fall into place. Yeah. So hopefully it does. Any questions on that one? All right, let's try another one here. So diboron trioxide reacts with water to form boric acid. So here you might have it all in words. So again, as I mentioned, we want to transform our words into proper formulas first, regardless of the balancing. So diboron trioxide, that is my type 3, right? So that's a B2O3 action. Reacts with water, which is H2O. And makes boric acid, which is this guy right here. So again, you see, I did not worry about balancing at this point. I got all of the proper formulas down. Now I'm going to balance, or you're going to balance. So yeah, let's take a look at this one. So we'll do the same thing. Reactants, products. In this case, we got boron, oxygen, and hydrogen. So on the left-hand side, we have 2 borons. Right-hand side, we have just 1. Left-hand side, we have 3 oxygens there, plus 1 more over here, which makes 4. Now, we do have parentheses and a number on the bottom here because we have a polyatomic ion, and this 3 gets distributed to both of the things in the parentheses there. So that would give us 3 of the oxygen. Left-hand side, we have 2 hydrogens, and once again, we would distribute that 3 in there for our hydrogen. Not much to work with in this case, so might as well start with the boron. So we're going to put a 2 in front. That 2 now also gets distributed to everybody in the behind it, including the stuff in the parentheses. So that means I have 2 borons. For the oxygens, I have 3 times 1, which is 3, and then 3 times 2 is 6. Yes, same thing here. 3 times 1 for the hydrogen, and then 3 times 2 is 6. So again, kind of in and then out in terms of multiplying those guys. And at that point, we can see we are done on the right-hand side. We clearly can't do much else over there. Going to our left-hand side here, in this case, once again, the easiest thing to fix is actually going to be the hydrogen, not the oxygen. Once again, oxygen's in a couple of places there on the left. So to fix the hydrogen, I would need to put a 3 right about there. And that's going to give me 2 borons. Oxygens is 3 here. And now I have 3 there, which gives me 6. And 3 times 2 is 6. So actually, by fixing the hydrogen, also fix the oxygen in that case. And we now have a balanced equation with a lot of arrows. Yes. Any questions on that one? So if you do have parentheses, you need to multiply in, and then if you put a coefficient in front, you need to multiply out and take care of both of those things. Any questions on that one there? Yeah. How did I get 6 on the production on the right-hand side or in the left? This side, yeah. Okay, yeah. So there's 3 oxygens there. And then over here, this 3 gets multiplied by the 1 here, which is 3. So 3 and 3 gives us 6 oxygens on that side. Okay, let's take a look, see how you're doing on this one, or you just maybe decide to go to the next problem, whichever one works better here. Let's see. So we got nitrogen, hydrogen, and oxygen. So left-hand side, we have 1 nitrogen. Right-hand side, we have 1. Left-hand side, we have 3 hydrogens, 2 on the right, and 2 oxygens on the left, and 1 oxygen there plus 1 more there makes 2. So actually in this case, everything's balanced except for the hydrogen. And in this case, you actually need to put a couple numbers, 1 on each side. Common number between 3 and 2 is 6, right? So we basically want to get everybody to 6. So hydrogen on the left to get to 6, we would need to put a 2, and hydrogen on the right to get to 6, we would need to lay up a 3. If we do that, we now, again, as this number goes to everybody behind, that's going to give us 2 nitrogens. That will give us 6 hydrogens and 2 oxygens. On the right-hand side, again, this number gets distributed as well. 1 nitrogen, 6 hydrogens, and oxygens. I have 1 here and 3 more here. So that gives me 4 that's happening in this case. So I screwed up everything else, but hey, fix the hydrogen. So that's a nice sign, I guess. Nitrogen seems much easier to fix at this point. So to fix the nitrogen, I'm going to put a 2 here. And that will give me 2 nitrogens, 6 hydrogens. Now, in terms of the oxygen, I got 2 there, and I still have the 3 there. That is 5 at this point, yeah. I clearly don't want to touch anything else. So the only thing I got to work with is the oxygen on the left, right? And that oxygen on the left is 2, I think. I need to turn a 2 into a 5, yes? And we could do that by perhaps using 5 over 2, for example. When I use 5 over 2, and I times it by 2, what do I end up with? 5. That works, I guess. So that's a 2, that's a 6, and that's a 5. Can I leave it like that, though? When you're all said and done, what does the coefficients has to be? They all has to be whole numbers. So this is a good example that you actually can use a fraction to balance it, but you do have to get rid of the fraction when it's all said and done. And sometimes this happens a lot when you have elements and a couple of things on one side and just the diatomic version of the element by itself is sometimes when this occurs. So if I want to get rid of the fraction, I should multiply everything by the denominator, which is 2 in this case. And if I do that, I will end up with 4NH3 plus 5O2 gives me 4NO, and I'm just multiplying that 2 all the way across to all the coefficients and 6 waters. And now I have a balanced equation that's all whole numbers, and we have 4 nitrogens on the left, 4 on the right, 12 hydrogens on the left, 12 on the right, 10 oxygens, 4 oxygens here, and 6 there is 10. How do you pick the right fraction? It's pretty simple. The number that goes up on top is the number we needed. So we needed 5, right? So that went up on top. The number on the bottom should always match this number. That way they cancel out. So you put the number you need on top. The number on the bottom should match that number. And that's the way you choose a proper fraction. So you could definitely use a fraction to balance an equation, but you do have to get rid of it by multiplying by the denominator. Don't pack up just yet. We got one more thing to look at. Yeah? All right. Any questions on this one here? All right, so lastly here in terms of balancing, I just want to go over this one with you just to show you one other thing that you can come across in terms of balancing. Let's say we have this form equation here where we wanted to balance this guy. Now, when we look at this guy, we might be scared because there's a lot of stuff going on, but there's a lot of stuff that we are familiar with. There's a lot of polyatomic ions in this one. So we have sulfate here, right? And we have sulfate here. We also have phosphate here and phosphate here. And sometimes when you have polyatomic ions that are the same on both sides in an equation, it's much easier not to go element by element, but to keep them together and sort of balance them as like whole units. So for example here, if I look at the phosphate on both sides, I have one PO4 on the left and one on the right. So that's good. If I look at the sulfate on the left, I got 3 here. And I only have one of those sulfates there. So that's where I would start. And to fix it, I would just need to put a 3 there. That is going to give me 3 of the sulfates. It also directly affects what element with sulfate? Silver. And that gives me how many silvers? And that's where I should go next. So I go back to the left-hand side. To make silver on the left 6, I would need to put a 2. That gives me 6 silvers. That then also directly affects the phosphate. I now have how many phosphates? 2, since it goes to this guy as well, right? So that's where I should go next. I go to the right-hand side, and to fix that, I should put a 2. That gives me 2 phosphates and how many irons? Which is good because that's what I need, yeah? And now you're balanced. So if you have an equation that has polyatomic ions on both sides, it's a lot of times easier to keep them together and sort of balance them as whole units. And once you balance the polyatomic ion, whatever it's hooked up to, that's where you go next. And you just kind of keep following from one to the next. At some point, if you do it correctly, everything should fall into place.